消耗的问题，是看随着那个第一堂课、第二堂课、第三堂课，学生人数越来越少。对啊，我是不在意啦，我的个性我觉得说你要来我欢迎你，不来你自己要那个进度要自己找的。对对对。那因为我在大学的时候，我翘的比那些没有来的学生还凶的。对，就我眼睛不好，我会先解释一下，不是鼓励你们翘课，因为我觉得我自己眼睛不好，没办法同时听课做笔记，然后还可以那个，所以这两件事，听课跟做笔记这两件事我没办法一起，所以我就干脆自己练。所以 anyway 好。So back to the our previous discussion about linearly independent. So we also define, okay, linearly dependent. Okay, so the vector v1 to bn, okay, are said to be linearly dependent if alpha 1 v1 plus r2 v2 plus blah 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 plus alpha n bn equal to 0 has not all zero solutions of alpha 1, alpha 2, alpha 1n. So there exists non-trivial solution, okay, for this linear combination. Okay, so this is obviously like just another way to say like linearly dependent, right? Independent, linearly dependent. So for example, okay, so E1, E2, E3, and 1, negative 2, 3. Okay, this one is similar to what we previously saw. Okay, we said these four vectors spin R3, right? But actually, these four vectors are linearly dependent because we can see like negative 1 E1 plus 2 E2 plus negative 3 E3 plus this 1 negative 2 3, okay, equal to 0. Basically, like, you just cancel out for every element. You just try to make sure that this unit vector cancel out like the corresponding element. That's it. Okay. So, and you can see that this assignment of negative 1, 2, negative 3, and 1. This alpha I assignment, okay, obviously are not zeros. Okay. So this is like an example that these vectors are linearly dependent. So there are some very interesting consequences here, okay, for linearly dependent. Okay. For example, if one of these VI's is zero, zero vector, then V1, V2 up to Vn are linearly dependent. Okay. So it is very easy to show this is the case. Okay, because say, without loss of duality, okay, say V1 is the one that is a zero vector. Okay. Without loss of duality, okay, that E1 zero vector. Okay, so we can just let alpha 1 to be 1 and alpha I to be 0, okay, for I not 1. Okay, obviously this one is 0, right? And this obviously will be an assignment where at least one of these alpha I is non-zero. Okay? In particular, alpha 1 is 1, right? It's not 0. Okay, so we have shown that okay, E1 to Bn okay, are linearly dependent. Okay, it is a zero vector. So in order to be linearly independent, okay, the set of vectors, okay, must not contain zero vector. Okay, so this is something you need to remember. And also, prove that if vectors E1 to Bn are linearly independent, okay, if this is the case, there exists a vector Vi, okay, such that Vi can be written as a linear combination of other vectors in this set. So this type of proof is relatively easy. Okay, you just like try to start from like the definition. That so we know like B1, B2, Bn are linear dependent. So in other words, there exists alpha 1, alpha 2, alpha n, not all 0. And alpha 1, E1 plus alpha 2, E2 plus plus alpha n, Pn equal to 0, right? This is according to the definition of linearly independent, right? Okay, so since these alpha I are not all 0, right? Not all 0, so there must exist one alpha I that is not 0, right? Okay, so we say alpha I is not 0. Okay, alpha I is not 0. Then we can say, we can write like alpha I, Vi will equal to negative alpha 1, E1 minus alpha 2, E2 minus da 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 da. Okay, minus alpha I minus 1, Vi minus 1, minus alpha I plus 1, V plus I plus 1, minus blah blah blah, minus alpha n, En, right? So we keep that alpha I on the left hand side and move all the other terms to the right. And then divide both sides by alpha I, because alpha I is non-zero. Okay, alpha I is not 0, so we can do that. So Vi will be negative alpha 1, alpha I minus E1. Okay, minus minus alpha I minus 1, alpha I Vi minus 1, minus alpha I plus 1, alpha I Vi minus blah 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 blah, minus alpha n, alpha I V n, right? So we can find okay, these terms that will linear combine the rest of the vectors to form EI. Okay, as long as alpha I is non-zero, because we need to divide both sides by alpha I. Okay, so alpha I has to be non-zero. Okay? So then given vectors alpha 1 to alpha n, okay, how can we verify they are linearly independent, not dependent? So here, okay, we are trying to solve this homogeneous linear system. This one could be zero. If there are non-trivial solutions, okay, then we know these vectors are linearly independent. Otherwise, these vectors, okay, will be linearly independent. Okay, so that's because homogeneous system must be solvable. It must be solvable. The only issue is there exists one solution or more than one. Or it has more than one, like it has infinite number. Okay, but I mean, basically, like we just need to try to solve this. I mean, this is like from the definition, actually from the definition, and you can write it as like I keep telling you, okay. I mean, when you learn the linear algebra, okay, this class, okay, majority part of the material is about matrix manipulation. So you try to understand it as from the point of the matrix point of view. So this one you can just write it like that. This is E1. This is E2. This is E3. You try to write it as a common vector for your for this matrix, and then you have this alpha 1, alpha 2, and alpha n equal to 0. So try to understand, try to see the thing from the matrix point of view. Okay. So let's look at some example. Which of following collections of vectors are linearly independent in R3? So if you try to write it, I mean, you can write it as like using like the previous of course, okay, no problem. But if you take my advice and write it as a matrix, then you will find that it's actually much more convenient, okay, especially when the matrix is square. Okay, so for example, the first one, 1, 1, 1, 1, 1, 0, 1, 0, 0, it becomes like 1, 1, 1, 1, 1, 0, 1, 0, 0, right? If you want, you can do it. And here, if you want to verify this is like it has a non-trivial solution, Then basically you just look at this square matrix. If it exists an inverse, say this is A, multiply A inverse on both sides. I mean, this A inverse multiplied by with A0. You know, you got 0. Okay, but this left hand side becomes alpha 1, alpha 2, alpha 3. So you have only one solution there. So the issue is whether or not A inverse exists. Okay, to see if this A inverse exists, okay, you just check if this matrix has like its determinant is non-zero or not. Okay, if the determinant of this matrix is non-zero, then yes, there there's only one trivial solution, and these three vectors are linearly independent. The second one, if you write it into matrix, you will find that, well, it's a 3 by 2. So it's not square. So if it's not square, okay, because first, we discussed this something similar to this earlier. Okay? From your first intuition is you cannot stay R3. But the second thing is that whether or not they are linearly independent, then basically you can easily verify. Okay, you don't need to use a matrix because this matrix is not square. You cannot do anything. So you just do like alpha 1 times the first one plus alpha 2 times the second one. Okay, equal to 0. You will see like So for example, you see alpha 1 will be 1. Alpha 2 will be 2. Okay, and the third element will show that alpha 1 will be 1. So in other words, okay, there's only one solution. Okay, so this is linearly independent. Okay, there are two vectors, they are linearly independent. But you just need to solve this. But if you solve this, you will find that alpha 1, alpha 2 are fixed to be 0, 0. Okay. And then the third one. This one, as I said, you just try to write it into a matrix. Okay, so it's 1, 2, 4. One, 2, 4, 2, 1, 3, and the third one is 4, 1, 1. So we try to see if it has like a non-trivial solution. And basically, again, as I said, you just try to verify if this matrix is determinant 0 or not, and you can answer that, right? Okay, so this one, as I said, you write it like this. See the S inverse. So relatively easy. Okay. So theory that x1 to xn the n vector Rn. Take a closer look. Here we have n vectors and it's Rn. Okay. So in other words, okay, if you write it like what we did earlier, okay, this capital X, which is represented by a column vector x1, x2, xn, it is a square matrix. Square matrix. The vector x1, x2, xn will be linearly dependent if and only x is single or its determinant is zero. Okay, so this one is like basically, if you try to understand it, this you write that definition into a matrix multiplication. So the issue is like whether or not the inverse exists or not. If the inverse exists, okay, then it means like you have a unique solution, which is like a zero vector. Otherwise, it does not exist. And when it has the inverse, it means that the determinant is not zero. Okay, so basically, like we have this. So vector L x1 to xn will be linearly independent if the determinant is not zero. So these two are independent. Okay. So determining whether the vector 4, 2, 3, 2, 1, 2, 3, 1, and 2, negative 5, 3 are linearly independent. Again, you just need to check the determinant of this 3 vector 4, 2, 3, 4, 2, 3, and 2, 3, 1, and 2, negative 5. Just try to get determinant. I'll stop here, okay, because like calculating like determinant of 3 by 3 matrix is this should be you should have learned that from high school, okay, or junior high. Okay, so I think I will just leave that to you. But basically, you can use this theorem, whatever we have discussed now, to determine like if these 3 vectors are linearly dependent. Okay. So that V1 to Vn vectors in a vector space V, a vector V in span V1 to Vn can be written uniquely as a linear combination of V1 to Vn if and only if V1 to Vn are linearly independent. Now we are trying to, what should I say, connect these two concepts. One is a span. Okay, we discussed span earlier, right? The other one is linearly independent. Okay, these two concepts actually have connections to each other. So this theory connect them. Okay, and this is the only way. So when you show both sides. So span can be written uniquely. Okay? This B eyes are linearly independent. So which side to start? From left to right or from right to left? First, let's do it from left to right first. Okay, from left to right. Because from left to right, it's very easy. Even though it doesn't look like easy, but actually it's easy. Because according to the definition of linearly independent, what we need to verify is alpha 1 d1 plus alpha 2 d2 plus blah 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 plus alpha n dn equal to 0. Okay, has only one solution, right? Where d alpha 1 equal to alpha 2 equal to blah 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 equal to alpha n equal to 0, right? There's only one such solution, right? Okay. So when I say it has only one solution, isn't that imply that remember, because from left to right, it means like any vector, its span can be written uniquely. Obviously, this is a vector, right? This is a vector in this subspace, in the space V. And this one is, you write a 0 as a span of these VI's, right? And this, when I say this span can be written uniquely, that, in other words, there's only one solution, right? It's equivalent to say there's only one solution, right? When I say span can be written uniquely, it means 0 can be written like that. There's only one solution, right? Otherwise, it's no longer unique, right? 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 And obviously, assigning di to be, alpha I to be 0 is one solution. Is that right? And since we said the solution is unique, then the alpha I to be 0 is the only and unique solution for this one, which would imply your V1 to be are linearly independent, right? According to the definition. Right? Right? So it's a given. It's a given. So now, okay, let's discuss the other way around. So we know they are linearly independent. V1 to Vn are linearly independent. And we want to show any vector, okay, it cannot be represented by more than one, like, linear combination. Okay, so say, I mean, so it's like B implies A, right? This is A, is B. Okay, so you guys still remember your discrete math class? How do we prove like B implies A? I mean, sometimes we so one way to do it is not A implies not B, right? Right? Okay. So I mean, let's say, okay, not okay, can be written as alpha 1 d1 plus alpha 2 d2 plus plus alpha n bn, and it has another way to write it, right? It's not unique. Beta 1 d1 plus plus beta n bn. There is more than one way to write it. Say this V has more than one way to write it, right? That's like a not B, sorry, not A, right? Not A, right? Can we imply it is linearly dependent? Because both of them are B, right? Both of them are B. So if you subtract alpha 1 by the lower one, if you try to do a subtraction, you get 0, right? That means V minus V, right? You get 0. So in other words, 0 equal to alpha 1 minus beta 1 d1 plus alpha 2 minus beta 2 d2 plus blah 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 plus alpha n minus beta n dn, right? 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 If we say there are two ways to assign this linear combination, that means this alpha, these pairs, they cannot be all equal, right? If they are all equal, I mean, we get 0, 0, 0, 0, 0 here. That means these two linear combinations are the same, right? But we say they are not unique, right? They are not unique. So at least one pair is the alpha and the beta I are different, right? So the alpha I minus beta I, there must be one term that is not equal, right? They are not. So one of the bi, its coefficient is not 0. So in other words, we have shown that B1 to Bn is linearly dependent, right? According to the definition. Because not A imply not B, that means we have proved B imply A, right? Right? 有个问题啊，我这样讲老半天，这个大家可以聊吗？我再用中文解释一次哦。你从左边到右边很简单，因为就任何的 span can written uniquely。那这个特别这个 span， 因为0也是一个 vector， 0的这个 span 也是可以被 written uniquely， 对不对？那既然可以被 written uniquely， 那代表说这个 alpha 1到 alpha n 只有一个解嘛。那既然只有一个解，我知道说 alpha 1等于 alpha 2等于一直等到等于 alpha n 等于0是一个解，那就代表什么？这就是唯一解，对不对？那唯一解的话，代表说这个是这等于这个 alpha 1到 alpha n 必须要是，那也就是说满足了 dependent 这个 linear independent 的这个 definition。啊，另外这个反过来的话，我们要证 B 传 B imply A，B imply A 直接证不太好弄哦。那比较简单就是 not B 啊，所以 not A 推到 not B， 我们知道这两个在逻辑上不一样。那 not A 就是说你这个存在有两个对同一个 B， 它的这个写出来的两个不一样的 linear combination， 那你把这两个互减一下，那因为它们不是它们这个。它是两个不一样的 linear combination， 所以其中某一个一定是减出来是归零。那这个左边是0嘛，右边这是 bi 的 linear combination， 那如果其中一项是不是零，那代表说它就是 linear dependent，linear dependent， 那就是推到大的 B 了。所以这个就让 A 推到那。这样可以吗？Okay. So we have it here. Okay. The proof I already told you the proof. So let's skip that. So last one. Okay. Function in Cn minus 1 A. Then f1 x, f2 x, blah blah blah, fn x. Okay. These are functions in Cn minus 1 A. Okay. If this f1, f1, f2, up to fn are linearly dependent, what does it mean by they are linearly dependent? Okay. It means we have the first one, right? The first row is given, right? Because we know that this f1 to fn, okay, they are linearly dependent. So they exist, the C1 to Cn, where they are not all zero. The linear combination of them is zero, right? Okay, the first row is given. The first row is given from this sentence. Okay, but if you have that, then remember these functions are differentiable, right? The Cn minus 1, they are in Cn minus 1, A, B. In other words, in this range, these functions are differentiable. So you differentiate on both sides. These Ci are still there, right? So you get rid of the second row. Equal to 0. And you can continue doing that up to this the last row, right? How many lines do we have? How many rows do we have? The first row is like a 0, right? 0 differentiation, 1 differentiation, blah, n minus 1 differentiation. So total we have n rows, right? We have n rows. Right? And we can write this whole thing in the form of matrix. So it becomes like this. Okay. And f1, f2, up to fn are functions in Cn minus 1 AG. Okay. So let me just write it. So if you write it in the matrix, the form matrix, then it's like f1, f2, fn, okay, f prime, f1 prime, f2 prime, fn prime, the f1, n minus 1, the fn, n minus 1 times c1, c2, cn equal to 0, right? If you write it in the matrix, the full matrix looks like writing what I wrote here, right? I basically just rewrite this like n rows in the form of the matrix. Let me see. So should be column match f1, f2, fn, we define this thing. Okay. We define this by what should I say Wronskian. Okay. Like we define this as a Wronskian function. Okay. It's a determinant completely. I mean, be very careful. Even though it looks like oh, this one is different from that one, right? It's different because like it's how should I say it's transpose, right? It's transpose. Okay. I mean, here previously like oh, these are linearly. No, we discussed the determinant. This one has to be 0 in order for this thing to be independent, linearly independent. But I mean, when it comes to determinant, the determinant of a matrix is the same as determinant of transpose of that matrix. We know that, right? So, I mean, you can write it like that, you can write it like here, it doesn't matter. Okay, so there exists a point x0, a, b, such that this one is not 0. If that's the case, then this one, this thing, are linearly independent. This is basically from from the fact that this thing is determinant is non-zero. If determinant is non-zero, then we know these functions are linearly independent. Okay. So we are pretty much this the last one that we will show. This thing are linearly independent. I'm running out of time. Let's do it next time. Okay, let's do it next time. Basically, we use the same thing here. So basically, we just show the first one is ex e negative x. Just differentiate. So ex differentiate to x by x, we get ex2. This e negative x we differentiate, get negative ex. Right? So we try to compute the determinant. So this one, well, basically we can get everything out. So it's when we check if this thing are how should I say 0 or not 0. So we can, this is just, we are considering just one negative one, right? Because this, we can get this out, common term out. So the something times this, right? This is non-zero factor times this. And this one is non-zero. Guarantee is non-zero. Right? So if this Wronskian is non-zero, then we have these two functions are linearly independent. And this one are linearly independent with P3. Actually, if you write it, it's going to be 1, 1, 1, 1, 1. And then differentiate becomes like a 0, 1, 2, 1, 1, 2, and 3, and 0. And then, okay, differentiate again. This one becomes 0, and then this one differentiate twice becomes 2. And it's 6. 0, 0. And the last one is become like 6. 0, 0, 0. So you try to consider this. 你就把每一个这个做微分嘛，一次微分，然后用它的这个0次项、1次项、2次项、3次项把它写在一起。第一次微分以后没有微分是1嘛，微分1次的话，第一项不见了 ，x 变1 ，2x 3x 平方，所以变成123再微分1次，那就变成这个就变成6x 0，2加6x，OK， 就变26，再微分1次就变6，然后是25，那就看这个。看说这个东西它是不是非零 ，OK， 如果是非零，那它就是 independent。You can show that this is they can determine this is not zero. You can easily show that. Okay. So we're done with this section 3. Okay. So next time we'll start from section 4. And next time, remember we'll do it online. Saturday morning. I want to remind you that we will, how should I say, the TA will send you like the meeting link. Okay, in the email. Okay, by e-class. So please check your email. Okay, careful. Okay, for the meeting link. Okay, for Saturday class. Okay, so that's it. Any questions? No question. I'll see you. Not see you. Okay, I'll see you online.